Okay. So, we will continue from this class. So, in the last class we talked about time domain OCT, then frequency domain OCT. So, same configuration which we had just seen in terms of free space diagrams. Now, if we see in terms of optical fiber based also, it is possible to couple the light through optical fiber, bring it to the. So, the of course, some applications may not need such arrangements, but there are some applications related to dermatology or endoscopy, etc., where we would like to incorporate OCT approach as well, let us say. Then optical fiber based approach helps us to make it compatible with those devices. So, the whole approach does not change even if it is time domain OCT or so frequency domain OCT, but this picture shows that we have an optical source. Okay, we can send an illumination pulse or or a broadband light source. When it passes through the optical splitter, so it is very similar to the beam splitter, but it also has a circulator approach. So, what happens, the input from 1 will couple to 2 and 3 through beam splitter, but when the return signal comes, it will couple to reflected signal will couple back to 4 circulator. So, it is acting as a circulator. Input from 1 gets to 2 and 3, while the reflected signal gets coupled to 4 through this beam splitter come circulator. So, this devices inside there will be optical components basically to ensure beam splitting operation, circulator, etc. Only thing is, it is in the compact form and coupled with the fiber. So, the type of beam splitter components, etc., very small size, they are coupled. So, the pulse goes, it goes to arm 2 and arm 3, and the reflected signal is to the detector, as we saw in case of time domain OCT in free space. And this signals reflected back from different surfaces of this tissue sample will be observed in terms of Z1, Z2, Z3 positions depending upon the reference mirror position. And only thing is, the path difference in free space is simply estimated based on the free space length L1 and L2, where refractive index is assumed to be 1, but in case of optical fiber, the refractive index of optical fiber will come into picture. So, N1 to etc. So, that much of the difference may be there. So, this is time domain OCT, and if it is spectral domain or frequency domain OCT, spectral domain or frequency domain OCT, we use a broadband light source. Same as the previous case, it goes through this reference arm and tissue arm through optical fiber, and the reflected signal is coupled to the spectrometer. Because spectrometer will provide us the spectral information of. So, basically if this frequency domain OCT has lambda 1, lambda 2 different wavelengths, multiple wavelengths, then for corresponding to each of this wavelength there will be some signal, integrated signal, correct, from different layers, etc., and then subsequently inverse Fourier transform of this will provide us the depth information of this different layers, Z1, Z2, Z3. Of course, it will be an optical path length, not the physical depth difference, but optical this difference will be provided. In case of swept source, S as a swept source. Of course, it is similar to the frequency domain. However, now instead of using spectrometer, what we are doing is we are using a tunable laser source. Okay. See, spectrometer converts all this, right, lambda 1, lambda 2, lambda, all these wavelengths into corresponding at different right detector point, we will have different wavelength output. In case of a swept source, detector need not be, it will not be a spectrometer, it is only a detector, but then what it does is it measures the reflected intensity of each of the waves lambda 1, lambda 2, lambda 3, etc., the detector base as the source is swept around. Okay. So, how to do this tuning? We already, if you can recall, right, different arrangements in using a fiber, using fiber brick grating or using diffraction grating, etc. We had learned tunable right sources. We can use such approaches and achieve a tunable light source, laser source. Here the main requirement is, although the spectral width is broad, but of this laser source, but it is tunable. So, each of these wavelength positions, it will be a narrow spectral output lambda 1, lambda 2, lambda 3, right. So, how will it look like? It will look like this, correct. Lambda 1, lambda 2, lambda 3, as you tune, as you change the wavelength, first lambda 1 will come, then lambda 2, lambda 3, as you tune, right, using tunable configuration, we will be able to tune each of this wavelength. Then they are all spectrally narrowed output. Okay. Very spectrally narrowed means spectral width is very narrow. The, if you can recall that the depth of in frequency domain, the depth of the sample, how much we can measure the depth direction depends upon the resolution of, also depends upon the resolution of the spectrometer. Okay, that is we already discussed a couple of 1 or 2 class back, right. Of course, scattering losses, absorption losses comes into picture. However, over and above the up to what that we can resolve in case of frequency domain also depends upon the spectral resolution of the spectrometer. Here spectral resolution of this tunable source as narrow as possible will be able to go into the depth, okay, direction. Okay. So, that you should be able to understand. Okay. So, these are the 3 main configurations which are useful for various right applications in terms of right swept source, frequency domain, OCT, etc., etc. Okay. Now, there is one more configuration which is of course based on either frequency domain or swept source, whatever, that is not a problem, time domain or whatever may be the approach, we can use it. However, the technique is also known as polarization sensitive OCT. It is a spatial arrangement, okay, of this OCT technique in order to remove or in order to characterize some type of tissues, either to remove the reflection from the front surface which is acting as a noise. See, whenever we keep, let us say I want to have the analysis of the tooth sample. Now, tooth enamel, the front surface is very high reflecting surface. So, the reflected beam from this surface will have a very large intensity. Okay. Now, if I go with a time domain OCT, I can expect that reflection will not appear as I go in the depth, right, Z1, Z2, then Z1 surface will not appear theoretically. However, because its reflection is so large, sometimes it acts as a noise. The intensity for that Z1 surface is such that although destructive interference will not or this interference pattern may not have very large effect, but still the signal is large enough which is acting as a noise for the Z3 surface to be identified. Okay. Or in some cases some of the material some of the biological right tissues, they have birefringence characteristics. Okay. That means as the light propagates through the medium, it's the light which is propagating through the medium will observe two different refractive index corresponding to the orientation of that tissue, etc. So, one wave, right, let us say if I divide this light into horizontal and vertical polarized light, let us assume that we have horizontal polarized light and vertically polarized horizontally polarized light and vertically polarized light. When they travel through the medium, depending upon the medium's refractive index along, right, depending upon the orientation along x axis, y axis, the speed with which the wave will propagate will be different. So, when you see the reflected signal, the polarization has changed by some amount. So, that polarization information may be useful for us to characterize some of the tissues or to identify certain characteristics. Hence, this PSOCT has evolved, right. It is also useful in not only in biomedical, various other applications as well, okay, mechanical or other electronic device characterization, etc. It is used. Now, so basically where it is used to visualize anisotropic structures, okay. Then to get the information related to the tissue characteristics, okay, tissue biological material characteristics in terms of its properties, okay. Then secondly, we can also use it in certain medium which is turbid, and then polarization states may be used to capture some information. And secondly, as I told you, the front surface of the sample, right, the reflection from this can be avoided as an extra noise signal for other depth information, okay. So, that can be avoided. And now, how this right system in terms of the polarization, etc. works. So, what I have done, just to something before we go into this right approach, just quickly before I describe this, I thought I will okay. One thing, right, can you recall quarter wave plate? Did you are you remembering this word, quarter wave plate? In the beginning, when we were talking about different optical approaches, I talked about polarization state and quarter wave plate. No, you cannot recall. Okay, okay. And so, it is like this. If a quarter wave plate is helpful, let us say I have vertically polarized light, okay, linearly polarized, maybe vertical polarization, okay, and or I have two components, okay, linearly polarized light, two components, vertical and horizontal, okay, from the same source, okay, right, and both of them are having right the same phase information, okay. Now, when it passes through a quarter wave plate, it has one axis which allows, this is let us say quarter wave plate, okay. It is a some glass material, okay. It has in F this axis, it allows light to propagate fast, okay. So, vertically polarized light, if there is a vertically polarized light, it will propagate fast, Okay. So, this is vertically polarized light. Okay. So, vertical polarized light when it travels through this quarter wave plate material, then quarter wave plate has been designated with f fast axis and slow axis, Okay. So, the vertically polarized light will move with us, it will experience relatively lesser refractive index, it will move fast indirectly, is not it. So, and horizontally polarized light will experience larger refractive index. So, it will move slow. So, this material is a birefringent material. Okay. It has refractive index in both the axes, different refractive indexes. Okay. If it is isotropic material, refractive index values will be the same, but this is not isotropic, it is anisotropic, and it has two components of this. Okay. Now, so what will happen? My at the input plane, okay, though my description may not be perfect, I will try. So, let us say right, both have the same phase, horizontal and vertical and horizontal waves, both have the same phase, right, same source. I just converted them into vertical component horizontal. Now, they are propagating through this material, okay, quarter wave plate. They have the same amplitude, here it is not so, but both the waves have the same amplitude. Let us assume, okay, this is quarter wave plate. So, if vertical one, right, moves faster, and quarter wave plate means it will move faster by the time it passes through this plate, it will move 90° ahead of the slow wave. Okay. So, what will happen now? We have a wave which is 90° ahead of slow wave, is not it? Now, if you see this, it is a circularly polarized light beam. It will move like this, helical, right, for us. The polarization state will keep on maximum here where 0 this is. So, vertical, then it goes like this, and while it is it okay? Can you imagine? So, this quarter wave plate helps us to convert vertically polarized light beam, right, to horizontal and vertical into two components, and then not into two components, but into circularly polarized light beam. Okay. Now, if I put one more quarter wave plate along the same direction, what will happen with the same orientation, okay, from fast axis, then it will move further 90°. So, what will happen then? Right, it will move by 90°, is not it? Now, what has happened? Right, with this, right, the phase has changed, and now if you see the orientation over here, let us say these two waves, vertical and horizontal, the resultant was in this direction, is not it, electrical field vector. Now, the resultant is in this direction, is not it, right. So, polarization state has rotated by 180°, is it okay? Are you understanding? Now, the same thing, if I put quarter wave plate as it is, this is the same, and I, instead of going forward, if I reverse this, okay, this signal reverses, okay, it comes through like this. What will happen? This fast will move fast. So, input is this, output will be the same as like this. Is it okay? If it is in the forward direction, 180 degree out of phase. If it is in the reverse, it reverses, it will become 0 once again, it will match, right. However, right, so this you remember, quarter wave plate. Two quarter wave plates combined is known as half wave plate, because it rotates by 180 degree, right, or it moves faster by 180 degree. Okay, is it okay? Are you? So, these materials are all birefringent materials. Okay, they have refractive index depending upon their axis, optical axis, all this. We did not go into details of how to estimate such refractive index, etc. We right, we did not go into those aspects, but we have assumed that there are such birefringent materials which allows us to do. When I am buying from right, for my device, right, I am not going to design the quarter wave plate fabricate, I will have to integrate it only, because so many components I cannot, right. So, that is why I am not going into those details, but it is, right, a possible. So, with this approach, it is like this. Okay. So, from the source, light comes, let us say it is a vertically polarized light beam, and it goes through quarter wave plate, which is 22.5 degree. 22.5 degree orientation. Okay. So, this wave which is travelling through will have vertical and horizontal component, but amplitude may change depending upon the orientation, it will get converted into elliptical wave, but when it passes back again, it will become circularly polarized. Okay. And the rotation, right, will be in the same this direction. However, on the sample side, so this is a sample, okay, sample, this is a reference, right, reference mirror. So, sample side 45 degree orientation we have kept. So, light horizontally polarized light, sorry, vertically polarized light which is coming from this beam splitter will get converted into circularly polarized light. Now, it passes through the sample. Okay. Now, sample refractive index, okay, in case of enamel tooth sample, the refractive index is different depending upon the polarization state. Okay. It is a slightly birefringent material, okay, tooth sample. So, if light goes through the sample and reflects back, right, because of some discontinuity, etc., what we will see is circularly polarized light got converted into elliptically polarized light, because the part depending upon the refractive index what it observes, some orientation of these waves changes in terms of polarization state when it is it is basically propagation speed changes. So, the phase changes, right, and that results into an elliptically polarized light beam as a resultant effect. And when it passes through this split 45 degree, what will happen now, this wave will get converted into opposite like this, okay, wave, because as you will see what I explained in the previous slide, it will help you to understand how that orientation will not move along the same direction, it will revert back, okay, it will revert. And now it has two components, horizontal and vertical, okay, two components. And this light, reflected light also from the reference mirror also has two components, horizontal and vertical, circularly polarized light, okay, and here it is elliptical. Only thing is that the component amplitude may be different in case of this, right, tooth sample reflection. So, the polarized beam splitter will allow horizontal component which is cross polarized component. Why cross polarized? I had sent vertical polarized light here, but now I am observing horizontal component as well, which is cross polarized, as well as I can also observe vertical polarized part which is co-polarized component. Both I will be able to observe, okay, using this. And then you may say, okay, what's the usefulness? So, if you can recall that when if there is a reflection from the surface, okay, it is not undergoing any polarization change effect, right. Birefringence it will not experience the surface, okay, it will only experience some reflection, from the surface. So, circular polarized light will remain circular polarized light, okay, approximately, and then you will see, you will be able to then get horizontal and vertical components like this. But if light propagates through inside, right, then the reflected one has a different polarization state due to birefringence it is observing within this tooth sample, and hence the surface reflection, right, major part of the surface reflection, right, which is basically a cross polarized, not cross polarized, right, it is surface reflection is maybe co-polarized reflection is removed from this. So, cross polarized component will only give us birefringence effect when it is travelling through the medium, okay, while co-polarized will give us multiple reflections inside from the front surface everything. So, noise component over here is available, is there, but here the noise component from the surface has been removed, okay, pass. So, that is the idea of using such polarization sensitive OCT. So, and you can think that if I want to make this compact, useful for certain applications, particularly dermatology applications, etc., or certain applications where birefringence characteristics are there, I have to convert this into optical fiber based system, so as to make it easy, flexible, you can easily move, right, the things you do not have to worry about alignment, etc., because optical fibers will anyway ensure that the light, right, propagates through a medium in a, right, and can be change direction, etc., easily. So, those things are challenging over here, okay, because polarization comes into picture. When light propagates through the optical fiber, polarization state may change. So, you need special type of fibers to ensure that the polarization of that light which is reflected back does not change. So, lots of good ideas, people are, right, working on such device development and its usefulness. Okay. By the way, right, as you already know that this system was established in 1990s. Okay. Today it is useful in various areas. Okay. So, technology wise it is still growing, right, and application wise enormous applications in biological, right, biomedical applications, etc. And so, there is a lot of scope in terms of even development, and one of the application is we can use it for endoscopy as well, similar approach, wherein optical fiber will bring the light here. So, sample arm will carry the optical fiber and endoscope will go to, let us say, a certain region, let us say gastroenterology, it will go to maybe passing through esophagus, will go through intense to stomach, etc. It can see the muscular means the tissue lining, right. Of course, the depth of penetration may be limited depending upon the depth of penetration may be limited. Why? Because it depends upon, as I told you, wavelength, tissue characteristics, etc. similar. And only thing is it will be millimeter order, sub-millimeter order, scattering may be quite different, etc. But the advantage is you do not have to remove that tissue sample from the, right. You can image the tissue sample without removing, without any tissue biopsy, you can still do optical approach of biopsy and observe what are the characteristics of those tissues, etc. So, endoscope has multiple tubes, etc., passing through these some channels. So, there is biopsy or suction channel, water tubes, air tube, optical fiber system, and some of the control wires to, right, move around by small distance. Then illuminating fiber is also required to provide some light, right. So, all this, right, is possible, illuminating source, reflected light, couples back, and this can be coupled right, with for intravascular imaging or for different applications, okay, related to gastroenterology, etc. I will try to show you some examples, but before that, the device configuration, how will it look like, right, when I send the light through endoscope? Just illuminating the surface and getting the signal is one way, but if I want to observe the let us say vessel, right, it is I want to observe the circumference, circular, right, all this tissues in different directions circular, then I will have to rotate this light. It cannot illuminate the object as it is, right, it has to illuminate the object in a peripheral, right, way. So, we need some configurations. These configurations are it looks very simple, but it is certainly challenging in terms of device, right. So, it has this size may be of the order of millimeter or so, or even less. So, it has reflector with a particular angle, light comes, it passes through the green lens will collimate the light. Okay. So, the optical light from the fiber is going to diverge, and if it is single mode fiber, what will be the divergence? Will be similar to the Gaussian beam divergence, correct. If it is a multi-mode fiber, divergence is approximately numerical aperture will decide the divergence of them. So, that diverged light, you before it goes diverge, it is coupled with the green lens is gradient index lens, okay. Its gradient refractive index is gradually changing, which will allow the light to become collimated. So, every wavelength, every such size will have a particular gradient, right, configuration. So, that is collimated light comes here, and as this torque coil which is rotating the optical fiber, or right, the whole device, the whole unit, not the optical fiber, the whole unit, then what will happen? The reflected signal will rotate around, is not it? The reflected signal will rotate. So, that is this rotation. It can be right, similar in endoscope. It can also allow scanning. So, by rotating this lens, the position will be different, accordingly it can allow scanning also across this. Okay. It has such different ideas to right, rotate the beam, and side exposure can be achieved with this, and the reflected signal from here couples back for our OCT, right, application through this optical. So, it is this approaches allows us volumetric imaging or circular, right, peripheral imaging of the vessels, etc. And right, there are different configurations. I have given some references over here. It can allow us to image, right, the tissue structure circumferentially. So, here it is some stomach tissues, it can right, capture this, it is a endo microscopy approach to visualize this, right. So, basically imaging the tissue structures, etc. It is of course, so different configurations, frequency domain, spectral domain, time domain, but coupled with optical fiber or coupling it with polarization sensitive ideas, approaches, or coupling it with endoscopy. All these different approaches are being worked out or being right, used for different such applications. Applications, as I told you, it is ophthalmology, it is very much used. Now, we did not imagine in 2005-6, we did not even imagine that the OCT, of course, people had started realizing that OCT is going to, but the cost of that OCT system was very high. It was very difficult to imagine that it will become now. Any of this eye clinic, if you go, they have imaging, because it can easily observe retina tissues, okay, and it can resolve the thickness layers to very right micron levels, few microns levels. So, that is so ophthalmology, gastroenterology, dermatology, endoscopic OCT, dentistry, etc. it is being used. Okay. So, application wise, now one quickly, oh, but time is there. Then if it is okay, to couple of minutes. So, one quickly OCT for ophthalmology, if I am using superluminescent diode with a wavelength around 800 nanometer, because it can easily penetrate through the lens and without much of losses goes up to the retina, and if the spectral width is 30 nanometer, I can achieve resolution thickness, right, resolution, layer by layer thickness resolution of the retinal structure of the order of 10 micrometer. But if I use titanium sapphire laser, which is a broadband, spectral width is very wide, I can achieve 3 micrometer. So, as small as 3 micrometer, but of course, the cost associated with it is tremendous. Okay. So, SLD will be in maybe 1000 or right, maybe maybe in terms of rupees, maybe 80,000 or 1 lakh rupees. Okay, source, broadband source. But if it is titanium sapphire laser, it will be in terms of crore. So, it is right 1 crore, 2 crore, depending upon the source requirement, size, etc. Power, output power requirement, maybe less than that also 1 crore, but around that very right 100 times. Okay, as per. So, depending upon our requirement, most of the ophthalmology applications they use superluminescent diode sources. Okay, or so, and then try to see the penetration. So, layer by layer information, this is colored image, refractive index change corresponding with the reflection peaks are being converted into color image, and not only that A scan, it is right B scan allows the full depth wise information of each layers of this ophthalmology. And if there is any some defect in terms of macular hole, some small defect, we can easily capture. If there is some let us say some fluid, right, accumulation beneath this retinal surface, it can be captured this information. Okay. So, some small hole, some this, right. So, it can easily be captured. So, actually if there is a normal tissue, you will not see such, right, A component at all, or this type of macular hole, etc. It is normal, it will have certain layers uniformly, right, laid down, but when there is such variation, it is captured. You can also capture in dentistry the tooth surface enamel sorry, or gum tissue, right, layers, etc. very easily, right, with this approaches. And we will continue in the next class some of the applications we will try to see quickly. Before we go to tomorrow, we will move towards therapeutic, right, applications. It is not to measure some characteristics or observe, right, tissue characteristics, but if we can use it to change the characteristics of the tissue or something using these, right, optical sources. So, such therapeutic applications also we will try to see as a biophotonics, right, device. So, with this, thank you very much. So, tomorrow we will continue with the class.